Good evening, participants. It's my pleasure to welcome Dr. Raveendra Gundlapalli. His title of the talk is going to be on AI and ML applications in battery performance predictions. About Dr. Raveendra, he is currently serving as Assistant Professor in the Department of Chemical Engineering, IIT BHU Varanasi. He received a PhD from IIT Madras and his research focuses on design and development of utility scale redox flow batteries. And he has developed 5 kilowatt and 10 kilowatt hour vanadium redox flow battery system, which is the first of its kind by them. The developed system has been field deployed integrating with solar PV at HPCL R&D campus, Bangalore. His work has been recognized by IIT Madras and published his research as a success story across several media. He continued the research at vFlowTech Singapore as R&D manager before joining as faculty at IIT BHU Varanasi. He has published around 15 journals and filed 4 patents. Additionally, he is contributing his services as reviewer across several SCI index journals and members of the editorial team of a few journals. He is exploring the research dimension in the verticals of energy storage, computational fluid dynamics, AI-driven innovation in battery management system, and the hydrogen economy with fuel cells and electrolyzer. Dr. Raveendra, we are looking forward to your session.
Thank you, Dr. Nalinkant and Dr. Rajesh for having me here. Let me begin my presentation. Thanks for your invitation and my introduction. I'm Raveendra. I'm from IIT BHU Varanasi. So I typically work on batteries.
Dr. Raveendra, can you increase the volume a little bit, or the volume is appropriate?
Maybe let me see whether it is.
Yeah.
Okay.
Yeah.
So Okay. Good. So I typically work on, as I mentioned, different types of verticals. I would work on energy storage, typically from redox flow batteries. So it conveys the other segment of lithium-ion battery. Lithium-ion battery, it's like a market-driven battery, which can be investigated by people from electrical engineering and material science and chemistry people. And we have the engineering of the batteries in the form of fuel cells, electrolyzers, and flow batteries, where the chemical mechanical engineers can have their research along with other people like electrical chemistry people and material science in addition to us. So I got an opportunity at IIT Madras to work on this kind of batteries, and now I'm extending the dimension to hybridization of the system by combining the electrolyzers and fuel cells along with flow batteries in a large-scale energy storage system. Okay, and recently, since the governance or the process or the operation of any industry or society is putting their hands and minds in the latest technologies like AI and ML, I also started my little exploration in what way I can have the application of the AI ML algorithms to predict the performance of my battery, because battery performance is typically complex. Now, that's why I have given in the part A that how typically the results will be, how typically, let's say if you want to charge a battery, how it is a function of so many parameters. I want to show that to you to understand that, okay, this is not so simple, like so linear. It is a function of so many operating parameters and so many design parameters. And in order to use AI and ML algorithm to predict that performance, which is a function of so many parameters, is not so easy, because people think that, let's say we have trained an ML algorithm by a set of data, we may assume that it will predict the performance for other scale, let's say other size. In 100 centimeter square cell, we have performed an experimental data and trained the ML using that data and calibrated it. And we may assume that it can predict the performance of the battery on a 200 centimeter square cell or 500 centimeter square cell. It won't be that much easy, because it's a function of area also. So I would like to show you how the AML can predict the performance and how complex it is. That's why I divided my lecture into 2 parts. Part where I will be giving you the technicalities of a flow battery, its performance characteristics, and what are my experimental and computational results. By giving you that complexity, I will start the lecture how AML can be used and what are the performance predictions I had recently. Okay. Now, this is very typical slide. See, if you want want to select which system I want to design to store the energy. If you want to devise a system for renewable energy storage, you have to see its parameters like intermittency, whether it is whether you are working, you are going for a large scale or small scale, or you are going for a singular hybrid, and whether you are applying for industrial or domestic transportation. And are you looking for instantaneous response like superconductors, capacitors? Are you looking for a large scale discharging like a 4 hour, 10 hour discharging? Or do you have a site restriction? Or do you have a connection of the grid? Or you are independent from the grid because of some localities like islands? So you have to see the parameters and choose the device which meets your parameters accordingly. So in a problem like multivariant problems like this, we have the much more advantage of AI and ML algorithms to choose a perfect device when there is a problem is a function of so many variables like this. So that's what I would like to start the session with this slide, where in order to choose a device to meet your demand, there are many parameters you need to consider. That's the complexity in the battery R&D. And just for an introduction, there are many ways you can store energy. Let's say you can store energy in the form of mechanical, like we always have a evergreen hydro storage. We have the lot of water reservoirs. We are depending megawatts of power electricity coming from the water reservoirs from last 50-60 years in India. And recently we have seen a lot of battery chemistries, a lot of batteries like lithium ion battery, lead acid batteries, and flow batteries, and metal layer batteries, where we have the market is driven by this kind of batteries. And we have the other kind of, we say AC is running from thermal storage. And all this, we have the phase change operation where the entire building is centralized AC. And we have instantaneous power is coming from the supercapacitors. Those kind of different energy storage devices are there. And this, the bottom one shows you how elaborately we came from a century ago to recent days. How the evolution happened in kinds of batteries are not new. They are developed in a century ago. Now even the flow battery is developed in 1950s. But the reality demonstration or the reality utilization of the flow battery has come into the market platform in 2010 or 2015, in that decade, in the last decade only. Because this, let's say, when can we use the lithium battery? When we have the demand for it. And typically, since the governments or the world ecosystem is looking to have the dependency on the renewables, and that is which is happening at large scale. And when we go for large scale, lithium ion batteries are no way suitable for it because they are not friendly devices like a customer oriented. It has a thermal runaway system, and it has the power and energy are coupled to each other, so that you cannot have the independent design of you cannot design a lithium ion battery for a solar park. Let's say we have a solar park of megawatts, you cannot design a lithium ion battery. So that's why flow batteries are coming into the picture as a competitor, as a friendly competitor to lithium ion battery, to have a large scale energy storage. So although it is developed in 1950s, the technology is taking the boom in 2020. Okay. Now, this is the picture. If you want to choose a device, let's say type of battery, if you want to device for a couple of minutes or hours, and at what scale of power, the batteries are segregated like this. And we say it's a Ragun power plot. It's very standard plot to segregate a battery based on your extent of time you want to discharge or extent of power you want to utilize from the battery. There are kinds of batteries along with storage, other storage like hydro storage and compressed air storage. So when you see flow batteries, the flow batteries are aiming at the high. When we really go for megawatt scale, your flow batteries are coming in picture. Although lithium battery is there up to 1 megawatt maximum, when we go for a solar power, which is like 100 megawatts at a minimum tens of megawatts. So you have to aim for a sodium sulfur batteries or flow batteries. These two are the very competitive compared to the lithium ion battery on a large scale. But the problem is when we see with respect to the size, density, how much power can be getting from a kg of the battery, how much energy we can obtain from the liter of the electrolyte. In that case, these are very low. And we anyway know that hydroelectricity is coming from the water reservoirs, water dams. They're very large. You cannot say that power is coming from a small battery like lithium ion battery. One same power cannot come from the same amount of volume of water. Typically, the flow batteries are also very negative in terms of its size. So that's why we recommend flow batteries for the large scale energy. So that's the story of this energy storage and flow batteries. And this slide shows you, let's say, the energy in a lead acid battery or a flow lithium-ion battery are stored inside a battery. Let's say if you want to, there is a solar PV at your rooftop, and your battery is fully charged, but still solar PV is available. If you want to charge the battery again, whatever the solar PV is available to you, you cannot charge because it is already limited. The energy is inside the battery. You cannot have a additional. If you want to charge again, you need to buy a new battery. But in case of flow battery, a battery is taking the charge of electrons, but all the amount of storage is happening in the liquid electrolyte, which is outside, like a diesel engine. If you want to perform the diesel engine, get the power from the diesel engine, if you put 10 liters, it may give you 10 hours. If you want to use the same diesel engine for 100 hours, you can just use the 100 liters of diesel, but the same diesel engine. Like that, we can have the same one battery, but you can have the lot of energy storage as per the existing by just increasing only the amount of electrolyte, not by putting a new battery. So that's the advantage of flow battery. This is the difference between the solid state and flow batteries. Okay. And when we see for a flow battery, since liquid electrolyte has to be circulated from the tank to the electrode, we need to provide a supporting plates, graphite plates, conducting graphite plates. So we need to have a local micro channels on the graphite plate to circulate the electrolyte. And the same design of local micro channels is applicable again back to the lithium-ion battery, where we need to have the thermal management of the lithium-ion battery, because in a stack you will be having 360 cells. You need to have the maintenance of temperature of those 360 cells. So you need to design the micro channels there. So the similar kind of micro channels is required for flow battery surface, where you need to distribute the electrolyte across the electrode. Electrode is anyway graphite felt in the form of porous felt. So this is the design of flow battery. And when any battery is same, you have a anode and cathode separated by a membrane. But since we are circulating the electrolyte from external to the inside the electrode, we need to have the pumping system. And this is how it looks like a flow battery cell in the laboratory. When we stack them up, this is the flow battery stack. When we make that stack into the system, inclusive of tanks and every kind of balance of plant, the piping network and everything, system will look like that. That's one system. When we take that one system to multi-scale for a solar park, this is how a flow battery energy storage plant look like in a real on-field deployment. So this is the scale we are really looking to have the development in any country for a solar park. So we need to start at a cell level to stack level to system level, and the field level deployment. This is the story for every battery, but here we have the independent design of amount of energy compared to the power. Power can be defined separately from the number of cells in a stack, and energy can be defined separately by taking the amount of electrolyte in the tank. But that is not possible in the lithium-ion battery because both are inside, both are coupled to each other. Okay. Now, for any battery, let's say if you want to see the performance of a battery, what one do? We'll have a charging of the battery and discharging of the battery. Any battery you take, lithium-ion or flow battery, or even fuel cells or electrolyzers, the typical curves will be like this. We have a charge curve and we have a discharge curve. Okay. Now, what are the restricting parameters? So which parameters will affect this performance? Initially, any battery will need to take absorb the electrons from the supply of electrons, and we have reactants there in the form of ionic species to capture that electron and store it and convert to another ionic species. Okay. Now, to initiate that reaction, we need to have some activation energy, and in the process of transporting the ions from one side to another side, so it may be micrometer length or millimeter length. So there is a transport of ionic species, both electrons or reactants or products. So there is a ohmic losses is happening, and towards the end, let's say there are continuous flow of electrons, because flow of electrons is very huge. The velocity is very high when compared to the flow of ionic species. It may be lithium ion or vanadium ion or whatever it is. So we need to accommodate equal number of ions, reactants, to capture the number of electrons we are passing through the wire. So that is not possible because all the reactants are converted to products, and we don't have the availability of reactants, so that the voltage, there will be more of voltage losses. It will shoot up like this. And at the time of shoot up, we say that there is a non-availability of the reactants to capture whatever the amount of electrons you are circulating to you are giving to the battery. So that's what we say, it's a mass transport resistance or fluidic resistance or concentration resistance, whatever it is. So these are the different phenomena we need to see and understand how a battery is giving you charging at what rate and how it is able to discharge. The difference between these two curves will give us the difference between these two curves will give us the voltage drop between the charge and discharge, and this higher this gap between these two curve, low will be the efficiency, and lower the gap between these two, you will have a very good efficiency. Let's say you charge any battery up to this point and again started to discharge. So the gap is only this much. Then your efficiency is very good. But what will happen? You are operating the battery at a very good efficiency. But what do you mean of it? The meaning is you are not utilizing the full capacity. The full capacity is somewhere here. So if you want to use that full capacity, and if you want to discharge its full capacity, the efficiency is becoming down. So if you use all the capacity of the battery, then your efficiency of the battery is less, and your life will become the less. So we need to understand till what level of cutoff we need to charge the battery, and so that we can discharge the battery efficiently. And this is one cycle. This is one cycle. And typically, lithium-ion battery claims that, let's say 5 years back, the number of life cycles a lithium-ion battery can give is only 1,000 cycles or 2,000 cycles. Now they improved very good. They are giving around 5,000 cycles by improving all this kinetics and understanding of the movement of ions, by providing the less voltage loss. So they are able to bring it up to 5,000 cycles as a lifetime. But even then, our flow battery is giving you a lot of, let's say, 10,000 to 15,000 life cycles, because the energy is stored outside the battery. So there won't be any contamination happening in the anode and cathode. So all are freely available outside the battery. So the life will be good. So because there is no intermixing of the anode and cathodic chemistry, which is happening in the lithium-ion battery. Okay. So you need to understand this phenomena, let's say activation energy, how the transport of ions is happening, how the availability of reactants to capture the electron. You need to understand this to improve the performance of any battery. Okay. Now, if you come to what is its physics or what is its chemistry, you need to how to say that battery is good or bad. You need to say what is its energy efficiency, what is its energy rating, how much energy is giving. Let's say if you take a mobile, if your cell phone, it has a battery, has a capacity of 4,000 milliampere hour, 3,000 milliampere hour. So how it is rated with the capacity. These two will give us how good the battery it is, how qualified the battery it is. Indirectly the subset of these two will give you how efficiently it captures the Coulombic efficiency, is how efficiently it captures the electrons. Let's say if you are giving 100 electrons, most of the batteries captures all the electrons. Let's say 98% of the electrons will be captured. And voltage efficiency is the real dragon here. It will kill the battery performance, because as I shown, the higher the gap between the charge and discharge curve will give you the less voltage efficiency. That's the main parameter which affects the energy efficiency. So we need to understand how energy efficiency, what is the energy rating, and how they are integrated by the voltage efficiency, which is indirectly a function of this Coulombic efficiency. Although Coulombic efficiency is 98%, if you operate at extreme conditions for any battery, extreme conditions, it may become 90% also. So that you are losing 10 number of ions per every 100 number of electrons. So you are losing a lot of current. Then voltage drop will be more. Delta V equal to IR. So voltage drop will be more. So they are depending on each other. But these parameters are the performance metrics, how they can be varied in a battery by studying what are like these logicals, activation energy, ohmic losses, concentration losses, how they are affecting your charge discharge behaviors. You have to study them, but they are all linked with the electrode. And there is when we are circulating the electrolyte, especially in flow batteries and fuel cells and the electrolyzers, we have a circulation losses. That's what we say, it's a pressure drop. So we are giving the pumping energy to the liquid. So we are consuming some amount of pumping energy. We needed that to go through the electrode. So we have a pressure drop. So we are losing some energy in the form of pressure drop. And as I told, between the anode and cathode, there may be intermixing of ionic species, anionic and cationic species, which we cannot control, because inside battery chemistry it is. There will be some crossover of anion and cationic species. You have to make them as low as possible to have the good life of battery. That's why the lithium-ion battery will have the less number of cycles compared to the flow battery, which is having 15,000 cycles. Lithium-ion battery is typically 5,000 plus life cycles. So this is the way one need to understand what are its performance parameters, how they are affected with the operating principles, and what are this component. These operating principles are governed by these components: membrane, electrolyte, electrode, and electrode is giving this phenomena. Electrolyte is giving all. Membrane is participating in the crossover of ions between the anode and cathode. So you have to understand all this physics and chemistry to improve efficiency of any battery, to improve the life of any battery. Okay. Now, if anyone wants to work on a flow battery, let me say, so everyone needs to start at a lab scale. Lab scale may be 10 centimeter square cell area or 100 centimeter square cell area. That can be the maximum. Beyond that, you need a more costly equipment facility. If you go for 600 to 600 centimeter square, that's what we typically require for field deploy. If you want to deploy the flow battery in the field to test, let's say if you have a EV charging station, you can charge the electric vehicle using the grid. But if you want to become independent of the grid, or if you want to become on the solar PV is there on your EV charging station, but you cannot charge directly from solar PV to EV batteries because it's seasonal or intermittent. You need to have a battery as a storage device between the solar PV and the electric vehicle charging station. So we can design a flow battery there as a storage device because it stores lot of energy. But the typical cell size should be the range of typical cell size, but you cannot have them at lab scale because you need to have a lot of expensive equipments to have this scale. We have those kind of facilities in IITs and research institutions. We are able to do that. And when we typically take from 100 centimeter square to 600 or whatever it is very easy in smaller number of cells to handle the electrolyte distribution. You have a low losses. There are no constraints in material availability. But what you cannot have the stack from that, because to get a kilowatt power, unless you have a kilowatt power, you cannot test for the renewable energy charging station. So you need to go for large sizes. For large sizes, you have so much of difficulties yourself you will be facing, because you need to distribute the electrolyte uniformly across the large size of the electrode. You have a lot of difficulty of leakage issues, materials constraints, and expensive, all those things. So you need to study both small scale and large scale to understand more and to see the results that it is needed for the renewable charging station. Then only come with AI or ML. I'm using my AI ML to predict the battery performance. Your renewable charging station will give you this much of efficiency if this is the operating condition. To have that real data for AI and ML, you need to work both on small scale and large scale cells. That's the purpose of this slide. Okay. So anyone, if let's say if you want to what kind of operating conditions, as I told, you need to select what is the flow rate required for the electrolyte, and what the current density is nothing but the flow rate of electrons. So you have a flow rate of electrolyte species from external tank to the electrodes. Similarly, you should have a flow of electricity from solar PV or grid or whatever it is. You need to define that flow. So are you giving 50 milliamps per centimeter square or 100 milliamps per centimeter square? Correspondingly, you need to define, take that I there. You will be giving as per the Faraday's law, you will be defining molar stoichiometric required amount of ions for the given number of electrons. So we will be defining that kind of stoichiometric factor from the taken electricity from this. So you can have that kind of factor, but one need to maintain minimum more than 3. So for every electron, if you give only one reactant, it cannot capture, because electrode is large surface area. As I told, the electrons can pass quickly, but not like a liquid cannot pass as the speed of the electrons. So you need to have minimum 3 times, 5 times of the number of electrons to have the good stability of the reaction kinetics. And each and every type of battery will have the cutoff voltages. For flow battery, we have a cutoff in the 1.8 in the charging. We can discharge up to 0.8. You can discharge up to down to 0 also, but life will become less. Similarly, in lithium-ion battery, we can discharge from we can charge up to 13.9 volts and discharge up to 12 volts, not below 12 volts. If it falls down from 12 volts, your life of the lithium-ion battery will go down. So there are cutoff voltages for charge and discharges. Let's say there are number of cells in a stack. You need to see whether the electrolyte is equally distributed to across all the cells. Then only each and every cell will give equal amount of voltage then only the voltage of the complete stack will be stabilized. Otherwise, there will be side reactions will happen. Let's say one cell is already reached 1.8, one cell is already 1 reach, other cell may be 1.45. Then what will happen? So other cell needs, it will be keep on the reaction, but other cell is already trying to go from 1.8 to 1.9. What will happen if you go beyond the voltage cutoffs? There is side reactions can happen, and this kind of precipitation of the electrolyte species on the electrode can happen. So we are stopping the movement of ionic species, and we have unnecessary precipitation, and we need to take out that electrode back and reassemble the battery. So we have side reactions in the form of carbon corrosion, or side reactions in the form of hydrogen evolution, or other kind of splitting of ions. We have a imbalance. Then we can have the crossover of the anode ions to the cathode ions, uh, which we cannot control. So we need to be very careful about choosing the operating conditions for any battery. Okay. Now let's say we compare three cell sizes, 400, 900, and 1500 centimeters square. These values are 1495 is not like a standard. When we really measure the exact area of the electrode while we design assemble mechanically by hands, the exact area came like 1495. That's the meaning of this. Okay, we aimed at 400, 900, and 1500 centimeters square, but we got this as the accurate area. Let's say we define some, as I mentioned, the required flow rate in terms of stoichiometry factor on a 400 centimeter square cell area. What flow rate is giving me good performance? Let's say flow rate of 3, no. Flow rate of 5, this one, and flow rate of 3 is this one. Flow rate of 3 is very low performance, and 5 is giving this one. And when you go to 11, this is my flow rate of 11. 11 times the flow of electrons. I need to maintain the reactance so that I will be getting very good performance. The gap between these two is less compared to this yellow line. Okay, and the extent of this is the voltage drop, and this is the capacity. So at SF3, I got this much of capacity. But if you go for SF11, I got this much of capacity. Capacity is increased, and voltage efficiency also increased. If I maintain stoichiometric factor of 11, okay. If I take these results and go for a stack level or train the ML, I may have different results. That's what I'm going to say here. If I choose the 900 centimeter square, what is the best flow rate required for a 900 centimeter square? It is around 7 or 9, and 11 is becoming 9 is becoming bad. 5 or 7, 5 or 7 are good. When we go for 9, it's becoming bad, and no matter of 11. And come to 1500, SF3 itself is good, and 5, 7 or 9 are reversing back. So if you really depend on the results on whatever happened on 400 centimeter square, and I am saying even 100 centimeter square is expensive. If I really want to go to 400 centimeter square, I need to have a equipment facility. And even by studying on 400 centimeter square, you cannot take the results straight away to the industrial scale, where we require typically around 900 centimeter square, 1000 centimeter square. And the same results are not linear in the 1500 centimeter square. So this is the real problems if you want to have the battery R&D, because we have the distribution of ionic species on the electrode nanostructure. The distribution we have to capture either through the kind of ANSYS COMSOL simulations, or really do a lot of experimentation on the typical practical sites, and then train the AML for the further prediction of the results. Okay. So one experimental way we have chosen to really do the experiments on a large size cells. So since we have the problem of electrolyte distribution across the electrode, that can be engineered by designing a local microchannels, I told. So there are different names of serpentine design, interdigitated design. This is very standard and very normal, but there are a lot of designs are available, microchannels, to have the distribution of ions equally across all the active sites of the electrode, so that we have the capture of electrons to it. So we need to design local microchannels. We say flow fields. It may be in fuel cells or electrolyzers or flow batteries. All we say it's a flow field. We are fielding the flow, okay, equally on the area of the electrode. So we will be having them designed on the supporting graphite plates. So let's say this is anode. Let's say this is cathode, and separated by a membrane, okay. And to have the distribution of the electrolyte from the tank, we have a supporting graphite plate. On the surface of it, we will be designing these two kind of flow fields. Why we need a flow fields? To distribute the electrolyte uniformly, to have a low pumping losses, and we need to evacuate the products from the electrode. there are reactants are forming as products, they have to come away. We have to give the way for the evacuation of the products. So if you design a perfect flow field, so they will give you the increase in energy efficiency, the densities of power and energy capacities, and they will decrease the pumping losses. They will decrease the resistance for the fluid flow. They will avoid the side reactions because of availability of reactants effectively. So this design is very important one, but we cannot do a lot of experimentation with many designs. We need to depend on simulations. Okay. So one of the tool I have used is a CFD simulations. I don't want to explain much on this. So let's say I have done some simulation on many areas, 100 centimeters square, 400,000, even 2000 centimeters square. Also, we have done simulations. So yeah, let's say if you want to do simulation on 1000 centimeters square, you need to have a computer of worth like 10 lakhs because you need to have a 200 GB RAM. We have done at IIT Madras and at Wipro Singapore also. So now these simulations will give you how the electrolyte will travel through the electrode. So one of the let's say this is my electrode. Okay, this is my flow channels. Okay, flow channels are going in this direction, and the electrode is like a area. So there is good distribution of ionic spaces over the entire depth of the electrode, over the entire width of the electrode, where there is a flow happening through the flow fields like this. There is a flow happening through the flow fields like this, and this flow micro channels are taking the electrolyte species by diffusion into the electrode porous structure, and this we have a good distribution. But see here, lot of electrode spaces are unutilized here in one of the design, in kind of interdigitated. In a kind of serpentine, we have a good distribution. But the problem is, each one will have advantage, each one will have disadvantage. The disadvantage of, we may say very low distribution in the IFF, but it will give you low pressure drop. There are both. This is the way, there is a uniform distribution like from starting to ending width of the electrode. Here is a maldistribution. So we need to see how effectively they are distributing so that you are able to design a flow field as per the local requirements. So if you compare them electrochemically, let's say what are its life cycles, IFF has given for the same conditions of battery, same flow rate, same operating conditions, the design of flow field like IFF, like interdigitated, the amount of capacity we are able to get only 17 ampere hours. Okay, but with the same thing with serpentine, we are able to get 33 ampere hours, and the efficiency is very good here. The efficiency means the lower the distance between these two is high efficiency. So there is a large voltage drop between the charge and discharge cycles for the IFF. So we have for the same operating condition and for same battery, if we have the local microchannels as a different design, which is very important to distribute the electrolyte to the electrode, you are getting a lot of performance variation, and this is the chemistry. I don't want to explain because these are a lot of non-Stein voltage differences are there, and the diffusion and convection is happening from the flow channels to electrode. I don't want to explain much of them. So because of there are chemistries available to diffuse the products and reactants back to the electrode and back to the electrolyte. This phenomena you need to understand as a chemical engineer and then design the microchannels. Okay. Now, let's say if you want to charge or discharge the battery at a different current densities, there is a flow of J is meant by current density, current flow, 25 amperes per centimeter square we are sending. Let's say at 100, we are sending 100 amperes per centimeter square like that. Okay. Now, if all other operating conditions are same, for a different flow of electrons, there is a difference in charge discharge behavior. At a low current density, the efficiency is very good. Okay. Although, let's say 3 current densities have given same amount of energy, the capacity, but their efficiencies are very different. So that's what we need to understand. For a different flow of electrons, we have different densities. Also, for different flow of reactants, efficiency may be same, typically approximately same for many of the flow rates, but the amount of capacity is different. That's what I want to say. When you vary the amount of the flow rate of electrons, the capacity is maybe same, but efficiency is different. When you have the different electrolyte flow rates, the efficiency may be same. The amount of energy what you are getting is different. So the efficiency is depending on the flow of electrons, and the extent of energy you are obtaining, you are able to store or obtaining is dependent on the flow of electrolyte species. Both should be optimized. So you need to have a lot of real data to train the ML. Okay. Now, by performing so many experiments like that, we came to know that when we really do a lot of experimentation on these two flow fields and both small scale cells and large scale cells, initially at a small scale size, IFF has given a very better performance. SFF is inferior than IFF, but on large scale, we proved that SFF is better. So what the summary of this slide is, whatever we obtain in a small scale cell size, it's not correct on a large scale cell size. We need to go really to the extent where the reality of the data comes. That data only you need to take to the A and ML. That's the meaningful of battery R&D. Then only, let's say if some person is training the ML with some data and he got that he is able to verify that ML with the remaining data that both the prediction and experimental data are correct, then he say that my ML code is very good. You cannot trust it unless you have the real data. And why I am telling you this, real data, it requires a lot of understanding of what is happening in a battery, how it is a function of so many parameters, and what you need to do at a different scales of experimentation. Then only a scientist can define what is the quality of the data. Okay. So when you go for a large number of cycles, so there is a disparate, let's say the power is coming like this at 600 watts. At some current, there is a more power is coming. So more power is coming. What is happening? The width of this cycle is high. Means width is high means time. Time means capacity. You have a high capacity at a low power, but if you want to operate at a high power, the amount of storage become less. So that amount of discharge can become less. So both are reverse to each other. If you want to operate the battery at high power, less energy you can store, and low power, more energy you can store. And sometimes there will be, that is with respect to the power to energy ratio. Let's say if you are operating at a constant power, there can be successful operation like this. So all the cycles are equally spreading, so there is no loss of efficiency. Every time you are getting a 400 watts in the discharge, nothing is happening. But sometimes battery may fail. Initially, it's giving you some kind of energy, but it's failing within, let's say, after 10 hours or 20 hours. So there are conditions like happening locally because of voltage drops. You need to capture the reasons behind it when the battery is becoming successful, when the battery is becoming failure. So there are conditions like this, power to energy ratios, success versus failure conditions. You need to capture them. Okay. Let's say if you take a look at the graph of what's called, what's the time now? It's 6:40. I think we still have some more time. Good. Let's say over 100 cycles, the capacity is coming down. That's the reality of any battery, because we have an internal crossover between the anode and cathode. We are losing the active species and the imbalances is happening. Whatever we can store at cycle 10, you cannot store the same at cycle 100. And you have that kind of variation. And the same thing at, let's say this is the cycle 2, and cycle 100 is giving only this much capacity. Cycle 200 is giving this much capacity. The logic of this graph is, when you see the data over first 100 cycles, the disparity, the ratio is this. When you see the data for the next 100 cycles, the disparity of the window is less. How can you train the ML? Let's say if you train the ML with the first 100 cycles, how can you predict the performance of this battery at 400 cycle? You cannot, because the disparity is becoming different at the first 100 cycles and second 100 cycles. There is a difference like this. And if you see that with respect to the electrolyte comparison, let's see in the first 100 cycle, there is the amount of electrolyte in the positive tank is increasing. So if electrolyte on one side is increasing, it is just coming from the other side. Whatever the amount of electrolyte on the anode side is decreasing, that's why it is traveling to the other side to the membrane. That's what we say crossover to the membrane. Because of this imbalance, there is a capacity loss we are facing. But what is happening after 100 cycles? The amount of electrolyte in anode or cathode are stable, constant. Why it was have a huge crossover in the first 100 cycles? Why there is a stability in the next 100 cycles? What is happening to its chemistry, and what will happen to the next 500 cycles? Because we are claiming the life of a battery as 5,000 cycles, 10,000 cycles. Unless we have the clarity of this understanding, Again, one cannot say that AML is not correct, because AML is like a kind of Maya. If you want to prove that Maya correct, you need to have the real data. Okay. Now, let's say if you want to operate, this is a field level result. Okay. This is done at HPCL R&D campus, Bangalore. We have connected my battery to the solar PV, real-time solar PV over a week, and this is the real-time profile. So let's say Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, like that. And we are able to charge the flow battery with the solar PV and discharge all the loads in that building with my flow battery. Anyway, this at the night time discharge is almost similar, because let's say we have 100 lights. All 100 lights is taking, every day we will be having 100 lights. That's why the discharge is almost constant like this. But charge, the availability of solar power is not in our hands. It may be different day by day. It's like this. But you have a different charging profile, constant discharging profile. So your flow battery or any battery needs to cope up with the different charging profile and constant discharging profile to maintain good energy, good efficiency. But we have advantage of independent P-by ratio in flow battery. You can define the power terms separately with the number of cells in the battery. We can define the energy rating in terms of number of liters of electrolyte in the outer side tanks, so that we can have a independent rating. We can design the power for the charging condition. We can design the amount of electrolyte for the discharging conditions, so that the number of failures in a real file, I don't have any failures, except in a very rare case, I don't have any failure. And the failure is also, I'm able to go up to 20% of SOC. Let's say in any typical lithium-ion battery, one needs to fully charge, and no one allows to charge down to 0% SOC. So people will have a cutoff of 10% SOC. Let's say if I have a cutoff of 20% SOC, so that cutoff is gone down only couple of times, very less amount of duration, very for a fraction of minutes. So you need to design this kind of batteries for large scale solar PV. You need to capture this kind of real data to see how the battery will perform in real time conditions, like solar PV connected when you using that battery for a EV charging station. So when can be the failure, how the P/E ratios changes with respect to the given profile load, profile of the power, or given profile of the discharge. Okay. Now, since we discussed, we see that what is the complexity of battery performance, how a battery will be giving you, will be taking the charge and giving discharge. It's a function of so many parameters. So it's a complex multivariable problem. It's a complex multivariable problem. One need to train, and that's one sector. And when you really look at the industrial sector, it's a battery, it's a overall, everyone is a circular economy. You have to start from the mining, production, assembling, usage, and recycling. When you really capture the system economics, not only on the battery performance, if you want to really capture the system economics from the starting scrap of the mining to the ending recycling process, that's circular economy, we say. So the difficulty will become more. And let's say if you want to have the permutation combinations and trial and error approach, there will be a lot of many possibilities, like so many petabytes. Our mind just have a capability of 10 petabytes. Let's say it is just nothing but 10 power 15. So there are this many possibilities. So our mind cannot handle those things. That's where we are loving, and we are bringing the AI into the sector where we can have the lot of automation of the processes with the help of AI. But only problem of AI or ML is to have the reality of the data, reality of the experiments. Unless a qualified scientist or qualified experimentalist confirms that data is correct, you cannot trust that this AI prediction is correct or not. Okay, so that's the complexity of any R&D, and everyone knows that what is AI and ML. AI is nothing but how we train the machines to think like a human intelligence, like think, learn, and make decisions like human. For that, you need to have the training with the data using by machine learning. Machine learning is a part of intelligence, artificial intelligence. So it defines the different types of patterns and gives that training and take a decision out of that patterns. And inside of it, you'll be having deep learning also. Deep learning is a subset of machine learning. So it will, instead of different patterns, it will go on a different multi-layer structure. so that it can algorithm you the multi-layer structures of different patterns, and different patterns will be given machine learning, and each pattern will be trained with artificial intelligence. So all are so machine learning will enrich the artificial intelligence, deep learning will enrich the machine learning, like that. Okay. Now, so as we have some highlight points of this AI and ML, so AI can use it to equip many modern digital devices. It will equip the speed of operation. It will equip the quality of operation by using AI. And commonly, how we design AI in the devices, this is nothing but we are learning from the experience. We are training the whatever happened in the past, and we are giving the data to it, and it is learning from the experience. But if you want, but the quality of it, the capabilities of ML algorithms, as I told, it depends on the quantity, quality, and variability of the data. That's more important. And we need to use this kind of disparity of data, qualified data, to train the ML, so that then only we say that the ML is trained, and we need to evaluate that trained ML to match with the one of the defined unknown data, so that we can, the performed experimental data, so that we can say that ML is trained. Okay, so we need to come up like this. And most of the people who are into the AI and ML knows the typical flow sheet of how it will works. We have a global set of data, and we train that ML by using by, let's say, by taking 70% of data. We need to take more data to train the ML, so that we will have the more accuracy, and then test data we will put to that trained ML. We will see how the results are, and the ML becomes supervised, and it may classify. Let's say there is a male and a female, there is red and black, yellow and green, like that. It will classify. Or otherwise, if there is a continuation of the data, if it is something is happening in 12th year, what will happen in the 14th year, what will happen in the 20th year, as per the behavior of the data. There is a continuous change like this. If someone wants to have the clarity, our battery performance, will it fall under classification or the regression? It will be on regression, because we are not classifying the performance. We are evaluating the performance. Let's say at a current flow of 50 milliamps, if it happens like this, what will happen at 70 milliamps, 100 milliamps, or 200 milliamps? It's a continuous performance measurements. The battery performance prediction will come on the regression analysis, not on the classification analysis. Okay. Now we have different types of machine learnings. Either we can supervise, like by training the ML, or we can simply unsupervise, because we don't be having the data. If you want to really go for molecular structure, how can we have the supervision of the data? You cannot have it. It's very difficult to have a lot of supervision, and we have to depend on the unsupervised data. But we will cluster the data. Let's say we will form different clustering of the data based on the sizes of the molecular structures, atoms, and we can segregate them. We can have the pictorial representation, how the different classification is happening, so that unsupervised learning can give you the classification instead of the regression. Okay. There is one more kind of algorithm, like reinforcement. Let's say we trained an ML. What will happen? It will give you the next prediction, but you need to take the feedback. You need to take the feedback. Let's say in signals and systems, one signal is passing like that in a system. You need to how the system responses for that signal. It may be process control or signals and systems for the many devices and electrical medical devices. How the signal is passed, what kind of signal is passed, and how the system responses. We will be taking the feedback again. Although ML is trained, we have to take the feedbacks of the systems on site and give the feedback to the ML, so that it will reinforce. We'll have the reinforcement of learning for the ML, so that we can have the more accuracy. So all three are like complementary to each other. Like it may be supervised or unsupervised or reinforcement. So all three mechanisms should be ready to train the machine. All these kind of algorithms you should learn. One should depend on all these three. You should not say that I will go with supervised learning. No, you have to. Some situation will come for unsupervised training, and some situations needed for reinforcement, like giving the feedback to the algorithm, so that it will increase the accuracy. All three should be complementary to each other, and you should one total algorithm of ML should have the three options. Okay. Now, there are different types of MLs. That's as I told, this is the way of process of ML, and there are many MLs. Let's say there are different methods of machine learning. Everyone knows very famous neural network, how the neurons pass the information in human brains. And let's say there is one kind of decision tree which divide the problem into n number of small problems, and one support vector machine which segregates what is the corresponding input for the corresponding output, what is the corresponding output for the corresponding input by having a hyperlane between them. And when there is one kind of nearest neighbors, let's say there is a similarity of the data. As I told in the molecular structure, if there is if you want to measure the atomic size and predict it, there is similarity of the atomic size, they will cluster out like this. So there may be kind of number of similarity structures available. The k number will be given, k and n. So there's a kind of passing the information through the networking, or segregating the corresponding output from the corresponding input, or solving the problem by minimizing its extent, or separating the molecular structure based on the sizes. So you have to choose suitable ML method for your application where you are in. Okay. And now let's say what is the typical application of ML and chemical engineering? So we can have many applications. Let's say you can what's called you need to discover about the material. You need to optimize the process operation, or you need to and these days we are working on sustainability, carbon capture, emission predictions. You need to see how efficiently, how green we are going with the process improvements. So in this kind of sustainability, when you really go for a multi verticals, let's say we are producing hydrogen from water. That's one chemical process. But that's not we are looking how we are producing the hydrogen. Is it green or blue, or how much emission we are happening? We need to measure the emission. What is the composition of the emission? What is the purity of hydrogen? If you want to bring in so many parameters, the problem is becoming complex. So for the complex problems, now we are bringing AI and ML algorithms to understand the complex problem, train them very well, and then predict the performance. Okay, this is the way AI and ML is helping the modern industrialization to sustain for the environmental goals, and to make it more smarter and responsive for the conditions what humans are facing. Okay. Now, how one can choose, one can start with to predict the performance of any battery by using the ML. One need to, so there are different steps. The main agenda is to, let's say if you have a curve, you need to measure a mathematical parameter is to find the area under the curve. By finding the area under the curve for any performance, it may be voltage versus capacity, power versus energy, voltage versus time, whatever it is. With respect to cell size, or with respect to flow rate, whatever it is, you will get some behavior of the graph from the experimental data. From that curve, you need to find out area under the curve. Okay. So more AU, if you are as per your ML algorithm, if any ML gives you the more AUC, so it is accurate as more. The prediction is very good. So that's the major objective, major aim you have to look at. And how you go ahead, you need to see the data collection, as I keep on saying so many things. So you need to have the collection of the data, and you need to pre-processing the data. So there are some anomalies, there are some errors, there are some iterative or repetitive kind of data, so that it will malfunction the training of the data. You are giving the wrong training to the ML by, if you are not pre-processing the data. You have to pre-process it. Then only you can have the area under the curve prediction analytically, and you have the data for the comparison and build the model. You have to write a code for the building the models. There are many models, like as we given in the last slide, there are many models, but you have to choose the corresponding model for your problem. Then you need to train that model, test it, how the AUC you are getting, and what kind of R-square value, what kind of mean square error, or RMS value of the error, or MS value of the error, whatever it is. There are many ways to characterize the data determinacy, whether it is determined to the actual data or whether it is very far away from the actual data. You need to go look at the R square values, MSE or RMSE also sometimes. Okay, that's the one set of training of ML. Now, either you have a reality of the data to have the good prediction from the ML, or there is one possibility to reduce the wrong prediction of ML by using the optimization techniques like genetic algorithms. So genetic algorithms will help you to segregate the data so that it will reduce the error. And in combination with the ML and the optimization techniques, combining the optimization techniques like genetic algorithms in the ML, it will reduce the error in the predictions. So loss predictions can be minimized. So this is one way where one can have the increased confidence on the prediction of ML if one uses the optimization algorithms with ML. Okay, if you don't have the reality of the data. Now, as there are many models, let's say like this, there are many ML models which depends on the transmission of the information, segregation of the inputs, outputs, and clustering based on the equality of sizes. So one need to see what is the problem type. Is it classification or regression? So are you classifying A versus B or expecting the next level of performance? So we need to choose that. So our battery performance comes under regression. So now that's what I mentioned here. So we need to see the data characteristics. Let's say if the data is small, if you have the small size of the data, you need to understand, you need to know the different types of ML models and their physical features, how they are helpful to different conditions. You need to have the knowledge. And one such decision is, if the data size is small, you have to go for a support vector machines ML model. If the data set is large, you can use the neural networks because it can handle the large number of data by neural networking. Okay, and the data should be clean. It should be then any model can be used. If it is noisy, then you have to depend on type of the model, because some models only will withstand the anomaly happening in the models. So you need to choose a kind of models like random forest. Random forest, it's like it's a spread over of the trees in forest randomly, so that although based on that structure, people have devised algorithm. So although there is a noisy, it may give you good prediction. But if the data is clean, any model can give, because linear regression, all those things are very simple. They will give good predictions. But if it is data is very non-linear or robust, then you have to go for random forest kind of ML algorithms. It's very typical. Okay, you have to see the performance priorities, whether you have the R square value or MSE values. So higher the R square value, let's say 0.99, you say that data is determinant. Data is very accurately matching with the experimental value. So my data and the model is very good. If you have the less number of mean square error, the MSE should be less, so that the standard deviation of the error, RMS value of the error should be less. So then we can say the model is very good. Okay, so this kind of knowledge one should have in mind to choose a model, to say whether the model is correct or not, to say whether the fitting is correct or not. Okay, now I have taken some experimental data. As I've given you in the first half, there are a lot of experimental curves I have given for a different alkylate flow rates, different stoichiometric flow factors. That the different flow factor means different alkylate flow rates. I'm sending at let's say 100 ml per minute or to 1 liter per minute, like that. I'm sending through the electrode, and so at this capacity, if I'm obtaining this capacity, the cell voltage is like this. This is my experimental data at a defined operating conditions. One set of operating conditions. This is what the experimental data I got. Now I use this experimental data to train a ML. Let's say I have taken the raw random forest, and I have taken the data to all the models also. Actually, I have used this data in all the models to see which model is good for me. So I have taken the analytical way to find out the area under the curve. I have used the trapezoidal rule, and for all those conditions of current flow rates, for a defined current flow rate, I may have different alkylate flow rates, like that. For a defined current flow rate, I have different alkylate flow rates. I have so many experiments. Let's say I have taken with the help of numerical methods and determine the area under the curve for each performance metric. Now I have determined that AUC using compare that AUC with the trained models with all this random forest, linear regression, decision tree, and all those things. See, my random forest has given very good R square value. Means out of this, the highest R square is obtained for the random forest, lowest M is obtained for the random forest. So why the linear regression has given minus value? Because see my performance, how the performance, is it linear? It's non-linear. It's completely non-linear. So you cannot have the R square value. You cannot predict the performance with linear regression. So it's giving out of boundary. The trained one has become wrong. So you have given the wrong training to the linear regression ML model. So it can be so in that way you can say that the result, the training is wrong. Because it's linear regression, one cannot go with the linear regression with such kind of nonlinear behavior. It's straightforward. So that's the appearance of negative values here. That's a proof for us. Okay, and you see how the mean square error is like 300 times like that. Okay. Now these are the results I obtained for so many ML models for the so many all these experimental curves. Okay. Now I can. Now for my battery performance, I can choose, yes, random forest has given me good predictions compared to other models. In that way, I can finalize the which model suits my battery. Maybe other models like gradient boosting may give good value for the lithium-ion battery because lithium-ion battery is chemistry different. Flow battery chemistry is different. And when you go for electrolyzers or fuel cells, their chemistry is slightly different. And so that you may have the different ML which is giving good predictions when I compare to flow battery. So for my flow battery, for my field of application, random forest has given me the good predictions. That's the way we need to segregate and finalize the prediction. So the whatever the table I have given here, I have given in the form of graphs. So I have the predicted values. I'm comparing with the actual values. Okay. So we should have the linearity like this, y equal to x. So to have the good predictions, and that is, so there is more deviation here. Let's say in kind of KNN model, there is more deviation here. If you choose with the linear regression, it's completely going away from my. The only one is random forest has given me much more linearity compared to other models. Okay. So in this way, I have finalized random forest has given me good prediction among the many ML models for my physics, for my problem. And now I am going to use that random forest to predict the performance on other areas. Okay. Now in order to increase the decrease the error, to increase the accuracy, I have included the optimization algorithms like genetic algorithms and Bayesian optimization, which depends on the probability, stochastic probabilities. So I have able to determine the optimal operating conditions. So let's say for a 90 current density of 90, 90 number of electrons are flowing per second, I need to maintain let's say 9 as a SF factor. This is the optimal prediction for this kind of current density. I need to have the this kind of flow rate. So both are optimized for a given flow of electrons. How much flow of electrolyte I should have. So based on that, I can optimize the operating conditions like that. Now I'll tell you. So the most operating conditions identified were, let's say for a current density of 90, I'm saying SF is 90. Okay. Now what is happening here? SF is people are saying SF 9 is very good. What happened to the original results for us? SF9 is bad in 900 centimeters square. SF9 is nowhere very bad for the 1500 centimeters square. SF9 is very good for the 400 centimeters square. Now that prediction is, I have predicted that performance using a random forest ML for 400 centimeters square. Even by having a lot of experimental data, a lot of optimization techniques involved in it, I'm able to prove that one of the ML model like random forest has given me for a current density of 90, my SF9 is giving me very good performance. I'm really happy. But what is happening? The same SF cannot be good for 1500 centimeter score, although I maintain same number of electrons, equal number of electrons for 400 versus 1500. So the SF9 is becoming bad results. Now I need to train I cannot trust, even now I cannot trust this random forest ML prediction, because the performance is a function of area also. That's the meaning. Although I'm saying I have done a very good job of training and predictions, including the optimization. I got SF9 as the optimal value. It is good for 400 centimeter square. But when we really go for a large scale, we need to train the same ML again with the data from the other cell sizes to come up with the accurate results. This is the way one has to utilize the AI and ML for the real conditions, and with improved data and more of qualitative scientific results to have the good predictions. Otherwise, one cannot trust predictions of AI and ML. That's the summary of my lecture. So thanks for everyone. So if anyone has, let's say, the questions, I'm really happy to answer you, or try to answer you, even if it is a difficult version of question, because there are different segments of people are there. Let me have any questions if you have. Number of participants has become 76.
Yeah,
in the middle
26. We started 26. Yeah.
And in the middle, there are so many noises are coming from the unmuting candidates. That's the very normal restriction for us in the online meetings. People will be at home.
I
and
took
having
care of
their
it,
own
Raveendra. No problem. I muted it whenever it is required.
Yeah, yes, I observed whenever there is a sound, immediately it's becoming off.
Yes.
Thanks for that.
I think you can check the chat box or some. I think we received some appreciation. The way you are explaining, some of appreciation was there.
Okay. Chat box.
Yeah, participants, please ask your questions. You can unmute and then speak, or you can put in the chat box.
I'm trying to open the chat box, but it's not opening to me. But actually, on the other side, I'm also a new candidate in the AI. I just started the AI from last 1 year. So it's really, it's a very, very diverse kind of field to understand it and apply this to your field.
Since you cannot, yeah. I have one question, Raveendra. On the previous slides, when you were trying to show the results based upon the optimization techniques, on what basis you are selecting? Because the area under the curve is maximum for surrogate model. You are not selecting that. And even in the optimal current density, we want to have maximum, which it comes through Bayesian optimization, right? Even if you look at optimal SF also, Bayesian optimization comes.
Yeah, right. Out of this four, these are optimization algorithms. All these four have given approximately equal one, and I have selected this surrogate model only. Surrogate model has given highest area under the curve, so I should choose surrogate model. But the advantage of the lucky what I got is every optimization techniques has given me approximately same window. They are the near window, although I took the surrogate model. But many of the optimization techniques are at the same level of predictions.
Okay.
Because
so you're
the ML,
you're saying you're close to 90 and 9. That's what
you're
trying to say.
Yes, I'm close to 90 and 9. That's the outcome. Why this much of accuracy came with the inclusive by so many algorithms means I have used the training of ML by the lot of data. I have used a lot of data to train that ML, so that when you really combine this ML with the genetic algorithm, optimization algorithms, so there is no much improvement in the prediction. All have given almost equal predictions because of the well-trained ML.
Okay.
Otherwise, there may be a disparity in the results. I don't know, maybe. So the main outcome of my lecture is I recommend one should not straight away trust the AML predictions. So one should go with the on what basis people have trained the AML. Let's say your student or your colleague, whatever he's doing in the AML, don't say that it is qualified unless you have a qualified data. That's the outcome of my understanding. That's what I'm going to give input.
Yeah, that's true. It actually needs a huge amount of data to have a very good machine learning model.
Any questions from participants? I think it will be nice.
Someone may be trying to ask. Or,
participants. Yeah. No, actually, this is the 4th day, right?
Okay,
Every day
people
we're sitting and people are spending their personal time.
are
Family
most
time
of the
has reduced
some
actually.
participants may be very well knowledge than me, but many of them are new to flow battery. I try to train them in flow battery also. So let's say somebody wants to work on flow battery or work on battery divisions, they need to understand how it is.
It's a new thing for me. I enjoyed your whatever the topics, the problem statement you're trying to define. The first part of your lecture is very, very informative, and you have presented very nicely. It's very clear for me. So that's what the comment says, that your explanation considers this. You can do this, or that's how you explain it. So it's the first of this kind. So many of the comments. So people are saying that's their comment. It's not. One of our participants is saying that. So thanks a lot, Dr. Raveendra.
Thanks to all the participants also like that.
Thank you, Raveendra, for your time, accepting our invitation and sharing your experience and knowledge here.
Okay.
Yeah. Thank you.
Okay, then.
Participants, you can provide the feedback. Okay, using the same link. Yeah.
And they can provide the feedback, and they can even write a mail if they have a specific questions. Okay.
Sure.
They can go through my mail address at IIT-BHU website. Right now, I'm guiding 3 PhD students and 4 MTech students. So we are working vigorously on flow batteries and electrolyzers. Now we just started our AI innovation with the flow batteries. So a lot of work establishment is happening now. Let's say in about next couple of years, I'll be full-fledgedly into the hybridization and of this energy storage systems. If anyone of the participants across the globe, if anyone wants to have a collaboration or understanding of energy storage systems, you can please contact me. We can have a discussion.
Thanks. We'll share your feedback, participants'
sure.
feedback to you.
Yeah, sure. Okay. Thank you.
Thank you. I'll stop recording.
Okay.
So
okay then.